we got a lot covered today. So, all right. So first of all, we had 2 lectures, right? 2 major things. Okay. So again, let me remind you that do not wait until the first assignment or the exam to study your notes, because engineering is something like math. Of course, we use a lot of math, and if you don't understand the first few things, and then you will find it's getting a lot harder to understand what's coming next. Okay, so the first few lectures, the first 2 lectures, a few major things we're going to use today. So first, Newton's law. Okay, so of course you have to understand what it means. Okay, so we use Newton's law to describe momentum transfer. Okay, so this can be interpreted as force or momentum flux, right? Okay, so viscosity and velocity. Okay, so we're going to use this today. And the definitions of the positive directions of the stress. Okay, and then lecture 2. So here we talk about the mechanisms for momentum transfer to occur. Okay, so this is the sort of molecular mechanism for momentum transfer. Okay, mainly due to the molecular interactions. So that's just one mechanism, and the other mechanism could be what? Convection. Okay, so momentum can be carried by mass. Okay, and then we learned how we are going to solve this kind of problems. So this is the major principle. Okay, so the change, of course, the change in the momentum in any control volume. Okay, equals V minus out plus generation minus consumption. Okay, so today we're going to look at how we use this principle and the appropriate boundary conditions to solve a problem. Since it's going to be the first problem we're going to look at, so we'll go very slowly, and because since it's the first, it involves a lot of new things. Okay, so raise your hand if you feel like we're going too fast, or you do not understand what I was trying to discuss. Okay, so this problem is called the steady state flow of a falling film. It's a very simple problem, okay, which is why I chose this as the first example. Okay, now of course the question is always why. Okay, why do we want to look at a problem like this? So I'm sure, if not all of you, some of you will have been to Six Flags, right? So this is the log fluid, right? Okay, so there is one right here. So basically, you're setting this, you go around circles, and then you get to the top, and then you come back down. Okay. So of course, the flowing water here, and that can be considered a falling film. Okay, falling fluid film. But basically, it's because if you look at the thickness of the water compared with the length and the width, the thickness is much smaller. Okay, so that's why it's called a falling film. Of course, we're studying this problem. So basically, when the water is flowing down slope, how momentum transfer is occurring, and what else? What other interesting things can we look at? Okay, so we're not just looking at this because you can have fun with it. Okay, so let me write down here this first. So we are going. Oh well, this is a little early. So anyway, so why do we need to look at this? Because other than that log flume, falling film is also used in the design of quite a few engineering devices, okay? So later, you will see a falling film blood oxygenator, okay? So as you know, this is a device that's used especially for open heart and lung surgeries, okay? So now falling film can be also used for reactors, okay? Microreactors or something, okay? So it can be also used in falling film evaporators. Okay, so that's why we're going to look at this problem. Okay, now of course. And this is what I was going to write. So this is a figure from the recommended textbook. I think I put this on Canvas already. So that's figure number 2.21. Okay. All right. So. We are not going to really care about how water or liquid got up there, okay? And this is the part we're looking at, okay? So a very thin layer of fluid flowing down a slope, okay? So as I mentioned before, so for the width, okay, we're going to assume that it's very large, okay, compared with the thickness of the fluid. So because of that, so basically, when this dimension is very large, like infinity, so basically what's going to happen is that no matter where you look at this, it's going to be the same. Okay, so basically, we can ignore that dimension, like that, the fluid within two plates problem. Okay, so that means we'll only have to deal with the length here. Well, we have to use that, and then the thickness. So we'll look at, because the water is flowing this way, the momentum transport is in this direction, so we cannot ignore that, okay? All right? So parameter is the length L, this angle beta. So in one of the homework problems, and there you will see a case where beta is 0. So basically straight down and, okay? All right, so other than that, disturbance at the entrance and the exit, so we're not consider those. Yeah, that's how you could look at it. Okay. Direction of gravity, of course, it's straight down. Okay. Okay. All right. So that's that, of course. And then this is how we simplify the problem, because we're not going to care how the water got up there and how after it got down where it goes. Okay, so this plate here where water flows, that's the only part we're going to look at. Okay, so then of course you have the liquid foam. So this is kind of like an enlarged view of the liquid foam. Okay, so now because we have to use diagrams, I have to draw it a little thicker than it's supposed to be. Okay. All right. So plate and fluid. And of course, we know it's flowing down, and there's velocity, there's mass, of course, there's momentum, and there's momentum transfer. Okay. So now, how do we solve this problem? Well, of course, before you solve any problem in engineering, you need what? You need equations. To solve equations, very often you need what? Coordinate systems. Okay? So to solve any problem, we need a coordinate system. In this case, you see the shape, okay? Straight, rectangle, obviously, we're going to choose the rectangle coordinate system. So no problem there. And of course, where is the origin and in which directions x, y, and z point to? So I'm going to use what's used in the book, okay? X and z, okay? So x and z. So that means the y direction is, if you have a right-handed system, y is coming out of the screen, okay? All right? And of course, we know the gravity is straight down, so that's the gravity. And the angle here between that direction and the plate here is theta. Okay? All right? Yes?
Why do you use z coordinate there?
Oh, it's basically because this was used by the book. It doesn't really matter if we use y, it's just the symbols will be a little different. I try to be consistent with the book, just in case you want to read the book, okay? All right, so x and z, okay? If you use y there, the symbols will be different, but it doesn't change, you know, the force and everything, okay? All right, so to solve this problem, of course, we learned or we discussed already that we need to use the shell balance method, okay? So change is equal to E minus out plus generation minus consumption and boundary conditions. To use the shell balance method, we have a coordinate system, and then we need to have what? A control volume. Okay, what's a control volume? Well, basically, it's a volumetric element that is representative of any volumetric element in this flow field, okay? In the fluid anyway, okay? So this volumetric element is arbitrary, okay? So basically, in this case, for example, we can select a small volumetric element like in an arbitrary position, okay? Anyway, okay? So I drew it there, but you know this volumetric element could be anywhere, okay? All right. So this way, whatever we can get from this volumetric element will be representative of everywhere in this flow, okay? All right. So. Of course, you know, in this dimension, so later we're going to use a width of the channel, okay, W. But still, right now it doesn't matter because in that direction nothing happens, okay. So, all right. So delta x and delta z, it's a very small volumetric element, okay. The two lengths in x and z directions, okay. So that's our volumetric element because. This is like, we simplified it to a 2D problem for, in this case, it's like a surface element, okay? All right? All right. So once that is chosen, of course, we need to use what? The shell balance method. Okay, so first step is to select a small volumetric element. So the length, okay. Delta y, well, it doesn't matter in this case, okay. So, and then we will consider the moment balance or conservation. In this case, it's in the z direction only, okay? Because we know the velocity is only what? In the z direction. So all we need to consider is the momentum conservation or change in the z direction, because we know in the x direction and in the y direction, there's no velocity, okay? Velocities are zero in those directions. So there's no need to consider any momentum change in that direction, okay? Now, of course, we need to consider this in this volumetric element that we've chosen. So let me use a larger diagram here to show you how we can do the moment balance in this small element, okay? So change, okay, equals in minus out plus generation and consumption minus consumption. So let me ask you, this is steady state. So which means we've started the flow for a while and everything has reached steady state. So in this case, for this control volume, do you think there's any change in the momentum in this control volume? I saw one person shaking head. Yeah.
I think so.
Why?
Because won't the velocity be faster, further away from the slide?
That's a good question. Is the velocity faster further down the slide? I know that's the experience you had while riding the log flume, right? So you know you started very slow on the top, but at the end you ended up very fast, right? Okay. However, if we consider the water flow only, just the water flow, no, I don't know what I think it's called where you ride it, but anyway, so nothing else, only the water, okay? So if you look, well, not because of that, you may think, well, there's gravity, right? So gravity is pulling this faster and faster, okay? Is that the case? Is water flowing faster? When we look at here and here. Well, think of it this way, okay? Think of this. Think of this. If here the velocity is faster, okay? Here it's slower. You should get a thinner and thinner thickness of the water, right? Because here it's going faster, and it's not fast enough, so that means there's less and less water in between, right? Okay. So this is a major concept that you will we will discuss later. That's because mass should be conserved. Okay, water is also a special sort of type of mass because it's almost incompressible. Okay, which means you cannot change its volume easily. So that means when this will flow faster, then this will get thin. Okay, so anyway, what I'm trying to say is that you probably guessed already, the velocity actually is the same here and there if you look at the water flow only. Okay, all right. All right. So with that out of the way, now again, in this control volume, so basically the velocity here and the velocity here will be the same, the velocity profile, okay? So, is there any change in the momentum in this control volume, steady state? So you probably know already there should be no change in the momentum, okay? All right, so in other words, momentum is conserved just like mass, okay? All right? All right, so basically change is equal to 0, okay? All right, now we still need to look at what? The in and out. So the net change is 0, okay? Does not mean things are not going in and out, okay? And does not mean there's no generation or consumption. It simply means that all these, they balance each other out, okay? All right, so we learned that momentum can be transported by what? Molecular interactions or convection, okay? All right, so when we look at this, the momentum that's going in and out of this control volume, the momentum that's being generated, okay, on this, in this volume, so they all balance each other out. So we'll first look at in and out, okay? So when you look at the momentum that's flowing in and out, so by what mechanism there the momentum is transported? So for example, when you look at the momentum is flowing in and the momentum is flowing out. In this case, well, you know already on this surface, because this surface what is in the same direction as the velocity. Okay, in other words, velocity is tangential to the surface, right? So that means that velocity will not have any contribution to the mass that's going into this volume, right? Okay, so on this surface, that means what? There's no momentum flowing in, right? Okay, the same the that surface, okay? So when you consider the momentum that's flowing in and out, only this one and that one. Now on this surface, of course, you know the velocity is going in that direction, right? So and here the velocity is perpendicular to the surface. So of course, mass is going in, and it's bringing in momentum. On this surface, velocity is going that way, perpendicular to the surface, but it's the mass is coming out. Okay, all right. So momentum is brought in here and brought out here. So which mechanism is this for momentum transport? Convection or molecular interactions? Convection, okay? So, all right, so that's why we discussed that formula we can use to calculate the amount or the momentum flux due to convection. So if you didn't study the lecture number 2, well, so far you probably are a little confused, okay? All right, so the momentum that's flowing in and out, okay? And then generation and consumption. What can generate momentum? Force, right? Okay, so force can generate momentum. When you look at the momentum generation or consumption in any control volume, all you need to look at is what? The forces that are acting on this control volume, okay? Just like what you've learned in 240, okay? So there, you look at all the forces acting on an isolated object, right? So here, because we're looking at momentum generation or consumption, all you need to look at are all the forces that are acting on this control volume, okay? So, what kind of forces are acting on the fluid here? Again, just like when you do force balance, okay? You think about the body force first, okay? Because these are inherent forces that basically are in all the masses, okay? So in this case, we do have gravity, okay? So gravity, as you've sort of suspected, can generate momentum, which why you think it can pull this fast and faster, but actually, at the beginning, that's the case, okay? But once it reaches steady state, it doesn't change anymore, okay? So that's because what? There are other forces that'll decrease the momentum generation by the gravity, and you'll see why, okay? All right, so we'll have gravity. What other forces can generate or consume momentum here, other than gravity? Gravity is a body force, right? It's like it's on every sort of molecule that's in there, the gravity. So that's there. That's the only sort of body force, which means in every point in it. So other than the body force, what else? What other forces do we need to consider? the surface forces, right? So in other words, this is a control volume. We also need to consider the forces that are acting on the surfaces, okay? All right? So in this case, we are only considering what? The momentum change in the z direction, okay? So we don't really have to consider the forces in other directions because, for example, a force in the x direction will not contribute to the momentum generation or consumption in the z direction, so we don't have to consider them, okay? All right? So these are in general how we're going to use the shell balance method. Now we can get into the details, okay? All right. So this is an arbitrary position. Well, let me do it differently. Sorry. So x. In other words, the coordinates at this point on the top right here, the coordinates there is x, z. Okay? So again, it's arbitrary. It could be any location in this following thought. Okay? So that's x and z. Because this length is what? Delta x. So that's why at this point the coordinate would be what? X plus delta x and z. Okay? This is the same z. Okay? So this point would be what? Z plus delta z. Okay? So in other words, the coordinates of this point is x, z plus delta z. So same x. Okay? So first, the coordinates of this point will be what? X plus delta x and z plus delta z. Okay? The four corners of this control volume. Okay? All right. So first, the in and out. So first, the amount of momentum. Remember, we're only considering the momentum in the z direction. Okay? So z component only, because there are no other components. So first, the amount of momentum that's flowing in. Okay. Obviously, we're talking about this surface, okay? The amount of momentum that's flowing in. Now, if you studied lecture number 2, this should come out very quickly. And in the end, before you get ready for the exam, you should be able to do this fairly quickly, okay? So, all right. So the amount of momentum that's flowing in. All right, so again, if you studied lecture number 2, you should be able to understand this quickly. Okay? Why? Why this is the amount of momentum that's flowing in from that surface?
Can you just clarify, what's the notation with the
Oh,
VZ?
yes, thank you. So v sub z, of course, that means the velocity in the z direction. This straight line means, with a z here, means this is the velocity at that location, coordinate. So in other words, it's the velocity on this surface, the coordinates are all z, right? So that's what it means, velocity at z. So times, of course, delta x, delta y, that's that surface, okay? Although you see a line, I kept talking about this is the surface because in this direction, the width, yeah, so that's like delta y. There's nothing happens in that direction, so, okay? The reason is what? Of course, you remember this, right? Rho velocity, velocity. For momentum transport due to convection, that's what? Momentum flux, okay? So flux is what? Momentum per time per area times the area of the surface will give us what? Momentum per time. Okay? So that's why this is the amount of momentum that's flowing in from that surface. Okay? The momentum per time. Okay? All right? So if you have a hard time of understanding why, go back to lecture number 2. Okay? So figure out the amount of mass going in, mass times velocity. Okay? All right? So then per time per area, so that you get a flux. Flux times the surface area, of course you get momentum per time. Yes?
Should it be delta x delta z or y? Is it in the delta y direction?
So delta x, delta z will give you what? This surface area.
Yeah.
But this is not the surface where the momentum is going in. Okay? So imagine it's a box, rectangular box. It's this surface here. Okay? All right? So delta y. So it's going in like this. Okay? Good question. Every question is a good question. Okay? So you ask questions now, it will decrease the amount of time you spend when you study the notes. Okay? So that's the amount that's going in. Okay? Now, of course, we talked about why there's no contribution from there and there, right? So no momentum is going in from those surfaces. And now, of course, the amount of momentum that's flowing out. Z component flowing out, of course, by that, we meant this surface where the momentum is coming out. Well, it's just like that, all right? Although the velocity notation will be a little different. So now the velocity at z plus delta z times vz, z plus delta z. And the cross-sectional area of that surface is still delta x, delta y. Okay? Yeah.
Do we have to assume for that first formula, do we have to, and I guess the second, do we have to assume that the momentum profile is constant across the whole z surface?
Good question. So,
Z plus delta z surface?
yeah, so that's a very good question. This is why I mentioned that this control element should be very small, so that if delta x is very small, you can consider there the velocity is more or less the same. Okay? Yeah, so in the x direction, you will see later, vz is not constant. Okay? However, as long as you select this element small enough, well, you can approximately assume vz is constant. Okay? So that's the control. I mean, that's a common thing to do when you use small volumetric elements. Okay. All right. So vz is changing in the z x direction, but if you select it small enough, well, it doesn't change much. Okay. So you won't have to consider this change in the x direction. All right. So since the velocity is equal to each other, you know what? You can see the amount that's going in is equal to the amount that's coming out. Okay? So that means in minus out, well, it's 0. Okay? All right. Now we just need to look at generation and consumption. So I mentioned that forces can generate momentum. So first, the body force. Okay? So we know that there's gravity. Okay? And how do you calculate gravity? Well, piece of cake, right? Rho delta x, delta y, delta z. So rho times volume, right? That will give us mass. So mass times G will give us gravitational force, right? So mass G, that's the gravitational force. And that's pointing straight down. Now in this case, since we're only considering what? The momentum generation in the z direction, okay? So we're considering the momentum generation in that direction. So that means we cannot use the total sort of magnitude of the gravity, right? Because we're not looking at the momentum generation in that direction. Instead, it's that direction, okay? Only one component of the gravity will generate momentum. It is that component, right? You look at this component, well, there's no movement in that direction, okay? So this is the direction we're looking at. So only one component will generate the momentum. And that component is the z component of the gravity, okay? So of course, you know that angle there is beta, okay? So z direction, this angle would be beta. So what's that component? Gravity times gravitational force times what? Cosine beta. Okay? Now, is this the momentum generated per time? We know this is the force, right? So m mass times g will give us something with a unit of force, okay, like Newton and something. Okay? So, does this term have the same unit as those? In other words, does this also represent momentum per time? Lecture number 1, okay? So there you will see something like force is equal to momentum per time. So exactly, this has the same unit as those. So this represents the momentum generated by this force per time. Okay? All right? So, what else? Well, body force is gone. There's no other forces. Of course, sometimes you may have to consider electric forces, magnetic forces. These are body forces too, but in this case, of course, there's no forces like those. Okay? So other than body forces, we need to consider what? The surface forces. Okay? All right. So first, this surface and that surface. Do we have shear forces on those, acting on those surfaces? Of course. Okay? Just like what we learned in 240. Okay, shear force is everywhere, not everywhere. I mean, as long as you have it there, it may have it here too. However, the shear force acting on the surface is acting in which direction? Tangential to the surface, right? Shear force. So that means what? The shear force here will be either in the x or negative x direction, right? So that means what? Well, no contribution to the momentum in the z direction, okay? So the same there, okay? Shear force will be either that or that direction, so no contribution to the momentum generation or consumption in the z direction, okay? So that means, well, we just have to consider the top surface and the bottom surface. All right, shear force. This is when the positive directions of the shear stress this is when that definition will be useful, okay? So this is where we're going to use those. Now, on the top surface, so we know z direction is this direction, no, sorry, x direction, z direction, okay? On this surface, the normal direction of the surface is pointing in which direction? So this surface. the normal direction of the surface is pointing in what direction? X,
X.
or negative x. Remember, this is the x direction. So look at the definition of the x. X is pointing here, okay? We're looking at this surface. So the normal direction is in the positive x direction or negative x direction. Remember, the normal direction of the surface is always outer normal direction, right? Negative x, right? So that's because, see, I don't want to draw the, I can draw it and mark it, I guess. So this is the normal direction of this surface on the top here. Normal direction of the surface, okay, top surface. See, that's x direction, okay? When you look at the outer normal, outer simply means what? You have to go from the inside the volume into the surface, okay? So that's the outer normal direction. That direction, of course, we know x as well, that direction, right? So this is, the normal direction of the surface is the negative x direction, okay? All right? Okay, all right. So on the surface, we have shear stress. Do we have tau zx or tau xz? So lecture number 1. The first index is what? Surface, okay? So, do we have tau xz or tau zx? Xz, right? Okay? So the first one, although in this case is negative x direction, should be the normal direction of the surface, so x. And the fourth direction would be what? The z direction. So we should have tau xz. Shear stress, okay? Tau xz at which location? What coordinate? You have the whole surface at which position? The whole surface you have the same x coordinate, right? Okay, so this tau xz would be the tau xz at x, okay? All right? If you're finding this difficult to understand, well, that means really you got to study the previous 2 lectures, okay? So tau xz at x. Do we know the direction of this shear stress? We don't, because we haven't solved the problem yet, okay? So before you know its direction, when you just write a symbol, you always assume what? It's positive, okay? Because you don't know it's positive or not. You assume it's positive, you solve the problem, and then you look at, is that larger than 0 or less than 0? If it's less than 0, that means opposite direction, okay? So you assume it's positive. If we assume it's positive, in which direction this shear stress or this force should point to? Positive z direction or negative z direction? Positive, okay. Remember, the way to remember that definition of the positive direction of the shear stress is what? Negative, positive, positive, negative. So in this case, the normal direction is pointing to the negative x direction. So that means if this stress is larger than 0, it would point to the positive z direction. So that's how you draw the direction of this force. Okay? So remember, this is just a normal direction, not a force. Okay? All right. So this force acting on this control volume will generate momentum. How much? We just need to convert the stress to what? To force, because we know force represents momentum time. Stress, how can we convert this to force? Stress is force per area. All we need to do is what? Multiply the stress by area. What's the surface area of this surface? We know this is delta z. Remember, this dimension is delta y, right? Okay, so. And of course, it's pointing to the z direction. It definitely what? Generates momentum, okay? All right, momentum generation plus tau xz at x, sorry. And times the area would be delta y and delta z, right? Okay. Now the bottom surface. The normal direction of the bottom surface points in which direction? Negative, positive or negative x? Positive, right? Okay. Look at the normal direction. Outer normal. So this is the normal direction of the bottom surface. So on the surface, I wish I had more room. Let me write it here. On the bottom surface, we have this stress acting on it. Again, tau xz, okay? First index, direction of the surface, okay? X or negative x. So x and z. At which location? Well, it's not x anymore because on this surface, all the x coordinates are the same at x plus delta x, right? Okay? So, if we assume this is this number is positive, in which direction the force points to? Negative or negative z, right? Okay, good. So that means for this one, we'll draw in that direction. So that's the shear stress. This one generates or consumes momentum. Consumes, okay? Because it's pointing to the negative z direction. If it's consumption, we need to take it out. X plus delta x, delta y, and z. So to convert this stress to momentum per time, of course, we need to multiply that by area. And that's it. Okay? We did not include the flowing in and out because we figured out already that those two are equal to each other, so they canceled out, okay? So we did not put them here. We put them here, well, it's zero energy, so, okay. Generation minus consumption. So this is the shell balance method. And that's the equation we're getting, okay? So, the delta y and delta z can cancel, right? All right. So that will be canceled. And then we can move the stress to the right side of the equation, okay? Let me write it, okay? So rho delta g cosine beta delta x is equal to tau xz at x plus delta x minus tau xz at x, right? So this is more straightforward, easier to look at. Okay, so what we're going to do next is to divide both sides by delta x, okay? If I divide both sides by delta x, here, this minus that divided by delta x. If I let delta x go to 0, what will the right-hand side become? Derivative, Okay, very good. So, divide both sides with delta x, and then let delta x go to 0. Remember, the small volumetric element. That's how small it is, okay? You let it get smaller, smaller, and smaller until that volumetric element becomes what? Almost the point. So since that volumetric element is arbitrary, so it can represent, so this point, right, can represent any point in the flow field, okay? So, and we get a derivative on the right hand side. So rho g cosine beta d tau x z dx. And here we go. We got the equation, okay? All right, so that's the equation. Of course, to solve it, we need what? Boundary conditions, okay? Boundary conditions. So we're trying to solve that stress tau xz, okay? So what are the boundary conditions we can use in this case? So of course, to look for boundary conditions, you need to look for them at boundary, okay? So what do you think?
So I was thinking that the shear, because the top interface is going to be with air, so that it'll be 0.
Yeah, that's
The
great.
shear should be 0.
Yeah, so here it's air, okay? So remember the last boundary condition we've discussed? If you have an air fluid interface, one common boundary condition is what? Because here it's like 0 viscosity, okay? So shear stress is 0 on the top. So at x equals 0, stress is 0. Do we need more? No, because this is just the first order ODE, right? So we only need one. It's a very simple equation to solve, right? You just need to integrate, okay? And you get this linear function plus a constant, okay? And of course, you use this boundary condition to determine that constant. It turns out to be 0, okay? So I skipped the steps. So if you forgot about how to solve a simple ODE like this, you gotta study a little bit, okay? All right, that's the solution. So that's the stress. As you can see, the stress is what? As long as x is the same, the stress is the same. Okay? All right? And also, since the volumetric element we chose is very small, like a point, okay? And this stress, or this equation, can be used to calculate the stress at any location in the flow field, right? Okay? This is why I emphasize that that volumetric element that you choose has to be arbitrary, can represent any location in the flow field, okay? So this can be applied at any location. Okay, so that's the stress. All right. So in momentum transport, you'll find that stress is not the only thing we're interested in. Okay. So in this case, for example, you're designing a log fluid. Okay, and you will want to know, you don't want to fail. Okay, you don't want it to fail. So that means whatever support you have underneath has to be strong enough, okay? All right? How do you know that support is strong enough? Of course, you need to consider the forces, okay? So the first thing we can do is to look at, well, for this whole plate here, when the fluid is flowing, how much force is being applied by the fluid to the plate. Okay? So we can calculate the force exerted by the fluid to the solid surface at x equal to delta. Delta is the thickness of the film. Okay, so basically this is delta, okay? So of course, the bottom surface here, it has to be x equal to delta, okay? This is the stress we're looking at, right? To calculate the force, all we need to do is to multiply the stress by the area, right? So since stress only depends on x, okay? Since on that surface x is all the same, z is changing, but only x is different. Only x is the same. So that means this is a constant on the surface, right? Okay. All right. So now, of course, the key is the direction. So in which direction I should draw this stress? Down or up? Yeah. You said up. Any other thoughts? Guesses? When we wrote this symbol earlier, I said, before you solve the problem, you don't know whether it's positive or negative, okay? So you assume it's positive, okay? And it turns out, well, we solved it, right? Okay, so rho g x cosine beta. X is all positive numbers in the flow field, right? Okay, so as you can see, it goes from x, goes from 0 to delta. So now we actually know this should be larger than 0, okay? Now, this is the surface we're looking at, okay? What's the normal direction of the surface? Negative x, okay? However, this is tau xz. It's larger than 0, right? So normal direction is the negative x direction. Then that means this force is in the z direction, okay? Actually, as long as you write this here, tau xz, you always draw the direction by assuming it's positive. Why? Because imagine if you have a negative number here, like -2, -3, okay? So that means you draw this direction, but this is what? -2 or 3, okay? Which simply means the actual force is up, okay? So anyway, as long as you write the symbol only, you always draw it direction like when it's positive, okay? If that number is actually negative, then that simply means the actual force or stress points to in the opposite direction. All right? Here we go. So direction and so. I know stress is a constant. You may think this is not necessary to write an integral like this, but I should get you into a good habit of doing these things properly so that you won't make mistakes later. Because sometimes this stress is not a constant, okay? It may change in the z and y direction. When that happens, you have to calculate this using integrals. Yes? So remember, the surface we're considering is this surface, not this one. Okay? This, not this one. So the plate, of course, has some thickness too, right? So we're considering the surface that's in contact with the fluid. So the normal direction of that surface is in the negative x direction. Okay? All right. So when the stress is changing, because everywhere is different, okay? Then you have to use what? Integrals, because it changes in z and y direction. So you integrate in the z direction and the y direction, okay? So we integrate in the z direction is from 0, z equals 0 to L, the whole length. And the width is from 0 to W, the width in the y direction. Of course, in this case, tau xz is a constant, of course, you know. When you integrate, you simply get rho g delta cosine beta times what? Width and length, right? So if tau x is a constant, of course, that's the simplest integral you can do. As a matter of fact, you don't have to do this, but just do this so that you know that you know how to do this when tau x is not constant, okay? What else can we do? We know the stress, we know the force, okay? In momentum transport, it's all about momentum, of course, all about mass, the scalar plus mass. So it's all about what? Velocity, okay? So we also want to know the velocity profile. So before this, we only know what? Velocity is not supposed to be constant. So how can we get the velocity profile? What relates stress and velocity together? Newton's law, right? So Newton's law relates the velocity and stress together. Although in this case, we don't have y, we have x, z. The velocity z is changing in the x direction, okay? So Newton's law that relates the velocity and stress together. For this case, will show up like this. Okay? So velocity gradient, velocity changing in the x direction, this fixed. Okay? So later we'll learn all the components. So far you're seeing the second component of the stress tensor. Okay? So of course we know tau xz. That's equal to rho g x and cosine beta. All right? So this is the ODE for velocity. Okay? Again, that's a very simple first order ODE. We'll need a boundary condition. So what's the boundary condition? Yeah.
For the solid fluid surface, solid velocity.
Sorry?
For the solid fluid.
Yeah. So basically he's talking about the bottom plate. Okay? That's where the fluid and solid sort of interface each other, right? Okay. The fluid solid interface where the the velocities should be equal to each other, right? But since the plate is not moving, that means what? The velocity at the bottom plate should be 0, okay? That's where x equals delta. Velocity z should be 0. So here we go. Only need one, right? Okay. So again, to solve this equation, what do you need to do? I'll skip all the steps, okay? So you divide both sides by negative mu. So this side will be negative rho g mu, rho g x cosine beta divided by mu. Then you what? You integrate, okay? So x will give you 1/2 x squared, right? Plus a constant. How do you determine that constant? Right here. When x equals delta, the velocity is 0, so constant plus or minus 1/2 rho g x squared cosine beta divided by mu. X, of course, is delta, plus that constant equal to 0. So this is how you get that constant, okay? Once you get that constant, you put it back into your solution, okay? So then, you have the velocity, which is equal to rho g delta squared mu and 2 y minus x over delta squared. Okay, so I rearranged some terms already. Okay, so you can see the x squared, delta squared, and you multiply that by this, you get the x squared term. 1 times that, well, that's exactly the constant you will solve for from there. Okay? So, although I skipped these steps, please do not skip these steps in the homework and exams. Okay? All right? Show details. All right? So, that's the velocity profile, where the velocity is the maximum. On the top, right? So, you can easily see that because this is a minus. X is larger, this is smaller. The smaller, this is larger, so obviously when x is the smallest, x equals 0, that's where the velocity is the largest on the top. It makes perfect sense, right? So, largest is the velocity when x equals 0, so rho g delta squared cosine beta to mu. Okay? What else do we want to know? Well, again, if you design this, you want to know how fast the fluid is flowing, right? So that you have the correct motor to drive the fluid up and everything, okay? So, and also about how much fluid you will need. So So the next common variable that people are interested in is the volumetric flow rate. Which refers to the volume of fluid that flows across the whole cross-section for time. So how much fluid is flowing across the whole cross-section? In this case, of course, the whole cross-section means which cross-section? Well, delta and W. So that cross-section where the fluid is going across, okay? Obviously, the fluid is not going that way, okay, or that way. The fluid is going this way. Of course, the cross-section means this cross-section that's perpendicular to the flow direction, okay? Otherwise, it's meaningless, this number, okay? Now, how do you do that? So we typically use Q to represent the volumetric fluid. How do you calculate the amount or the volume of the fluid that's going across the whole cross-section? A. This is how you do it. Because Vz is not a constant, right, in the x direction or at different locations of the cross-section. It changes with x or z. In this case, only changes with x, okay? So you select a small area, dA, on the cross-section, okay? All right? And then Vz, so the velocity times that cross-sectional area, small area, will give you what? Volume per second, right? Okay? So the whole cross-section is like this whole piece of paper like this, right? So you know the velocity is all different on the surface. How do you calculate the volumetric flow rate? So you select a very small area, dA, okay, very small, so that Vz is more or less a constant. You know on that dA, volumetric, so the amount of the volume of the fluid that's going across is what? Vz dA, okay, right? Volume per second, okay? All right. So we discussed this when we discussed momentum transport by convection, right? All right. Because we talked about how much mass is flowing across, right? So this times density will give you mass per time. Of course, for the whole cross section, you need to do what? Surface integral. You need to integrate over the whole surface to get the total volumetric fluid. Okay. There is another way to write this. So you know that on the top here is still the same as here, only add these two. So of course, you know, if you integrate dA over the whole area, you simply get the area of the cross-section, right? Okay? All right? However, the volume divided by the whole cross-section will give us what? Volume per second divided by the whole cross-section. So this is the amount of total amount of fluid going across the cross-section. Okay, total amount of fluid divided by the area. That's the concept of average velocity, right? Okay. Of course, that times this integral, that's area. Okay. So now you can see the volumetric flow rate is equal to what? average velocity times the whole cross-sectional area. Okay? All right? All right, now we can do this. So for dA, the cross-section, so this cross-section, it's dx and dy, right? Okay? So it's dx and dy, the cross-section. That's how you do the integral. So, because now velocity is not a constant, so remember now we have to do the integral. So for the y, from 0 to w, for x is 0 to delta. And we have the velocity rho g delta squared cosine beta 2 mu y minus x over delta squared dx and dy. Okay? So velocity dx dy. That's dA. Okay? Alright? A small surface element. Dx dy. Right? Okay? So you can do this integral, right? Okay? So you get x here, x cubed, 1/3, plug in the numbers for x. Y doesn't matter because it does not depend on y, you just have to multiply that by w. Okay? So again, let me skip the details. Delta cubed w cosine beta and 3 mu. So that's the volumetric flow rate. Okay? And of course, once you know the volumetric flow rate, you can calculate the average velocity easily. So the average velocity is Q divided by the whole cross-sectional area, which is what? Delta times the width, right? So delta and W. So we have rho g delta squared, W is gone, cosine beta, and 3 mu. As you know, the maximum velocity is rho g delta squared cosine beta divided by 2 mu. And average velocity is divided by 3 mu. So you know this is equal to 2/3 of the maximum velocity, the average velocity. Okay? I don't have much time left, so I'll stop here. But remember, this solution that we got. Okay, so later on will be used for a discussion about blood oxygenated. Okay, so anyway, there are a few things, discussion points we need to consider, but most of the equations are done. Okay, so again, don't study until it's too late. Okay, all right, so that's for the